Take your time now and read the instructions because you don't want to waste your time on the exam reading paragraphs like this. The most important piece of information is we're only allowed to use butene as the source of carbon. So before you do any synthesis problems, just observe what's given to you and take some notes to the side. We're given 1 butene here, which is a 4-carbon compound. And we're asked to synthesize 3-methyl-3-heptanol, that's an 8-carbon compound. So in some way we need to modify 1 butene in 2 different ways so that we have a nucleophile that can attack a 4-carbon electrophile, of course oxygen containing, to result this 8-carbon compound. The first thing that I can think of is an alkynyl anion. And like we said, that could be used to attack a 4-carbon compound that's electrophilic enough. Now this 4-carbon nucleophile can attack another 4-carbon electrophile to form this 8-carbon compound. The dead giveaway that the electrophile is a ketone is because we have a tertiary carbon here. At this stage, if you have a tertiary carbon and your starting material is an alkene, the first thing you should think of is an alkynyl anion that could attack a ketone. That's where this methyl group comes from. So even though we might have 5 to 6 steps, the goal is to create this anion, this nucleophile, and this electrophile, and link them up together. Now another thing is that we don't have any degree of unsaturation in this compound, so it's very likely that we need to carry out some sort of reduction at the very end. So to start, let's use 1 butene and form the alkynyl anion. The first thing to do is to carry out halogenation. And that's accomplished by Br2 as a reagent and dichloromethane, inert solvent. That should form a vicinal dihalide like this. In the second step, we can use that same vicinal dihalide and introduce 3 moles of sodium amide base dissolved in liquid ammonia. And that should give us our 4-carbon alkynyl anion. So let's just reserve this on the side for now and call this compound 1. So we said we need to form the anion, but now we need to form a ketone, which is the electrophile. So let's carry that out in step 3. We'll take our anion and do an aqueous workup in water. That's to protonate this terminal carbon, forming the alkyne. And with this alkyne, I can carry out a hydration reaction, that's Markovnikov. That's by using mercuric sulfate dissolved in aqueous acid. So I'll use H2SO4 in water. That should form a 4-carbon ketone like this, a methyl ketone. Remember that the oxygen here has 2 lone pairs, and because of oxygen's electronegativity, there's always a net dipole pointing upwards that withdraws electrons from this carbon here. That's why we say the carbonyl carbon is partially positive or electrophilic. And that's perfect when we have an alkynyl anion. If we mix the 2 together, they should link up and form an alcohol. So that's the next step. And let's call the ketone compound 2. The nucleophilic attack needs to have an aprotic solvent, so DMSO works, or any sort of ether. I'll use THF as my ether. And that should form the following product. Remember, we have 4 carbons here and 4 carbons here, so the compound should have a total of 8 carbons. But the longest carbon chain is 7. And that's because if I have my alkyne and my ketone, the alkyne will come in and attack the carbonyl carbon, sending a pair of electrons up like that, which would form something like this, with a negative charge on the oxygen. But if we carry out a second step, meaning we let this reaction go to completion in ether and protonate it with an aqueous solution like water, we can form the OH group here. So I can save myself some steps and do an aqueous workup after the nucleophilic attack. Now this compound here is very similar to what we're given here. We have a 7-carbon chain here and a tertiary carbon because of the methyl. Here I have the same thing. I have a 7-carbon chain as well and a methyl group that makes this tertiary. But we're still not done because here I have no pi bonds. I have no degree of unsaturation. So just like we said in the beginning, some sort of reduction needs to be carried out. And to reduce an alkyne to a simple alkane, we need to use catalytic hydrogenation. So let's say this is compound 3. I need 2 moles of H2 on a platinum catalyst. And that should give us our final compound, a 7-carbon chain like this with the OH tertiary.